So I want to look at some couple other examples of how we can use Newton's method. Of course, we looked at it in the last video how this recursive way of defining successive iterations, right, that get closer and closer to the true root of a function, essentially the solution to the function f of x, or the output, the input that makes the output of the function 0. And so here I want to look at solving equations. Look at this equation here. How can we use Newton's method to solve this equation? Think about trying to solve this equation algebraically. We'd have a lot of trouble. We have an algebraic term here. You might think, oh, we can use the quadratic formula, but lo and behold, there's this sine of x here. And so there's an algebraic and a trigonometric function coupled in this equation. It makes it really impossible to solve with any of the techniques that we have. So how would I, find the solution to this? Again, in this day and age with technology and calculators, we take it for granted we can use their abilities. We might have an equation solver, but again, this course is not so much about how to be a button pusher, but how that equation solver might possibly work. And so that's what we want to look at. How would we find this? And so the question is, how does this relate to Newton's method? Well, here's the idea. If I have an equation, I can bring all the terms over to one side of the equation. For instance, this 3 can be brought over by subtracting 3 from both sides, right? And then what do I have? I have this equivalent equation. Subtracting 3 from both sides gives me this. This equation is equivalent, meaning the solution to this equation is the same as the solution to the equation we started with. And so if you'll notice, if I now just simply call this the function f of x, notice I have f of x equals 0. I'm looking for the 0 of this function. So that brings me back to Newton's method. And that's how we can solve for this. Okay. Now, if you actually graph this function, you'll see that there are a couple roots. And so let's just take a look at the graph of this function real quick. It's a trig function. I want to make sure I'm in radian mode, which I am. And I'm just going to enter in this function. And let's see what window I have to view that in. Let's zoom. Let's just do a decimal zoom window. I think I want to do that. Okay. It almost looks like a parabola, which kind of makes sense because the sine of x term in this function, it only has a value that varies, what, between 1 and -1, right? The sine of x is between 1 and -1. So that value I'm covering up is somewhere between 1 and -1. The rest of it is what, x squared minus 3. All right, so x squared minus 3, we know what that graph looks like. A graph of a parabola opening upward. Basically x squared shifted 3 units down. But we have this little wiggle in there, right? Sine of x wiggles around between 1 and -1. So it looks almost like a parabola, but it's a little distorted. Do you see that? So at any rate, the key is that we have 2 roots, right? And with the zoom window I have, each tick mark is 1. So it looks like my solution has 2. One is close to two different solutions. One is close to x equal 2, right? And then the other is between -1 and -2. Okay. What I'm going to do in this case is I'm just going to estimate this positive root, which looks to be very close to 2. In fact, that's my initial guess. I'm going to try. I'm going to try and see if x equal 2 works, and start there as my initial guess in the process. Okay. One thing I don't want to do is, if I'm trying to estimate the positive root, you don't want to choose too close to the negative root, right? If you choose a value close to 2, Newton's method generally is going to help you converge to that root, that positive root. If you choose a number like, what, about -1.5 or somewhere around there, hopefully you would then converge to this root. One thing you want to be careful is not to choose anything around this area, because down here, it kind of goes off the screen here, but there's going to be a horizontal tangent line, and we know what happens in the last video. If the derivative is equal to 0, the entire, since we're dividing by the derivative here, that thing will will not work. And so there are those sort of things you need to think about in getting started. A lot of times the problems that you're asked to do, they give you an initial guess to start with. If not, again, looking at the graph of the function and choosing something close to the root you're looking for is the way to go. Okay, so that's what we're going to do. We're gonna find the positive root, and so my initial guess is going to be 2, as I said. Now, in the process of finding my next iteration, of course, I'm not going to let n be 0, so I've got x of 0. I can find f of x of 0 because this is f of x, but I need f prime, right? So let's go ahead and find f prime of x, which is pretty easy. If this is the function f of x, its derivative is 2x. And what's the derivative of sine of x? That's cosine of x. Derivative of 3 is 0. So there's my derivative, very easy. Okay, and so what's x of 1 going to be? Right. What's going to be x of 0 minus f of x of 0 over f prime of x of 0. Right. Okay, and what's x of 0? It's 2, so I can plug in 2 minus f of 2 over f prime of 2. Okay, so what I'm going to do is I'm going to again use my calculator to do these approximations, do these iterations each time like I showed in the video last time. So let's go here, and the way we start is we start with that initial guess. Initial guess x of 0 is 2. So I just hit in 2, right, and hit enter. Of course I get 2 back. The point is I'm storing 2, and remember, into the answer field. Okay, into the answer field. Now what I want to do is do 2, or answer, right? Right, the x of 0 is what I'm doing, answer. Everywhere I have x of 0, I'm plugging in answer. Answer minus, and in parentheses, f of answer. So what's f of answer? Here's f of x. So that's going to be answer squared minus sine of what? The answer, minus 3. Close parentheses. So that's the numerator, right, of the expression, right? Up here, f of 2, and then divided by f prime of 2. So divided by, in parentheses, f prime of 2, replace x with x of 0, or in the calculator with answer. 2 times the answer minus cosine of the answer. Close parentheses. And again, in the very beginning, if you remember, I checked to make sure I'm in radian mode. Anytime you're dealing with a trig function, make sure you're in radian mode, or you're going to get incorrect results. Okay, so hopefully everything looks good. So now when I press enter, I'm going to evaluate this expression here and get my value for x of 1. And let's write this out. 1.979, etc. all the way down to there. So there's our our first iteration, if you will, x of 1. Okay, and then we'll continue the process. So what will x of 2 be? Well, x of 2 will be x of 1 minus f of x of 1 over f prime of x of 1. Right? And so x of 1 is this value. Okay, but the quick thing is, right, with the way we did it, right, remember in the calculator, is now I can use the entry command. So don't forget, entry is right above the enter key. If I do second entry, I recopy this whole expression, which is now, though, answers what? This value, right? This value, which is x of 1. So now I'm evaluating this expression here, x of 1 minus f of x of 1 divided by f prime of x of 1, and that gives me x of 2. Okay. In the instructions, it was asked to find the solution accurate to the 7th decimal place. And so as we're continuing this process, we're looking, if I compare these two answers, well, this one's accurate to what? To about the 3rd decimal place, right? Because the 4th decimal place differs. Okay, so far we're accurate to about, looks like, the 3rd decimal place. Okay, So what's x sub 3 now? I won't write all that. It's going to be what x sub 2 minus f of x sub 2 over f prime of x sub 2. But we can do this real quick with the calculator. Just hit entry, and now x sub answer has the value of x sub 2 in it. So this will give me x sub 3. And x sub 3, let's see, compared with x sub 2, looks like we're accurate all the way out to here. 1, 2, 3, 4, 5, 6, 7. So it looks like it's pretty well accurate to 7. There could be a slight change in that 7th digit, so let's just double check. We'll do x sub 4, entry, and then enter. And you see x sub 4 is the identical in the calculator to x sub 3. So it looks like we have our answer 2 for decimal places. So the positive solution to our equation, there's two solutions, remember, is 1.9793201 to 7 decimal places, right? And this is to 7 decimal places. So again, we can't get an exact solution, but you know, in all intents and purposes, we can get as accurate as essentially we need it to be in this process. So the negative root would be found similarly. The negative solution is found similarly. What would you plug in there? Probably what, negative 1.5. Let's just do that real quick in the calculator, and I'll show you how we can do this. So I can do negative 1.5, hit enter. That puts that into the answer. Now I have to do second entry. I have to do it twice. Second entry. That brings up the previous the second one, which again is this formula now. With this is our new x sub 0. That was close to the, remember the negative root was close to negative 1.5. So I plug that in to Newton's iteration, and I get x sub 1. There's x sub 1, entry, enter. There's x sub 2, entry, enter, and pretty much, right, we're almost identical, right? Certainly out to 7 decimal places. So about negative 1.4183101, I guess, if we want to round that up because of the 9 there. But at any rate, or to either way, we've got it at least to 7 decimal places here. So pretty quick convergence in this case to the roots, to the solutions to this equation. And so you might understand maybe how the equation solvers and calculators and other algebraic software, how those are programmed to work. And so if you're a computer science person, this is important for you to know how those things work. Okay. Again, probably some modified form of that. Okay, is being used. So let's look at one last example here. And my last example is, let's find the square root of 7 accurate to the 7th decimal place. Okay, you say, how is Newton's method going to come into play there? Where's f of x equals 0 there? First of all, let me just say, some of you are just saying, well, I'll just take my calculator and hit the square root of 7. Again, that's a button pusher. Yeah, you can do that, but how's the calculator doing that? Okay, what's a method it might be using? Okay, probably not Newton's method. I don't know. Just think about if you had to answer that question, 100 years ago, before we had computers and technology, or even 60, 50 years ago almost. There were algorithms people had to use, right, to be able to find the square root of 7, or different techniques and methods to estimate. Now, square root of 7 is not bad, but square root of 3,921. I don't know if that's a perfect square or not, but that would be very challenging to do. So here's the way we're gonna do this though. I'm gonna be looking for the square root of 7, so I'm gonna let the variable x be the square root of 7. Okay. You see, I've got an equation. Hey, we can just subtract the square root of 7 and set it equal to 0. Well, the problem is in that process, your function will have the square root of 7 in it. We're trying to estimate the square root of 7. You can't estimate the square root of 7 having the square root of 7 in the function you're trying to use to estimate it. So here's the trick. If x is equal to the square root of 7, what's x squared equal to? If I square both sides of this equation, x squared equals 7. Now I can say what x squared minus 7 equals 0, like I just did with the equation, and this is my new f of x. Therefore, f prime of x is what? The derivative of x squared minus 7 is 2x. Okay. And if I wanted to estimate a starting point, let's think about this. I know the square root of 4 is 2, and the square root of 9 is 3. So the square root of 7 is somewhere between 2 and 3, right? And since 9 is closer to 7 than 4, my initial guess I'm going to use is 3. I'm going to use 3. Okay, so it's somewhere between 2 and 3. I think it's a little bit closer to 3 than 2, but here's my estimate. Okay, and so we go back into calculator. So let's clear all this stuff out. So remember how we start? We start with 3, store that into answer. And then what's my x of 1 going to be? It's going to be 3 minus f of 3 over f prime of 3. Okay, and again, I'm going to use the calculator to do this. So, of course, I'm going to use answer, right? So I'm going to have answer minus, in parentheses, what's f of 3? That's just answer squared minus 7. That's the numerator, right? And the denominator is 2 times the answer, so divided by, in parentheses, 2 times the answer. Make sure you put those numerators and denominators in parentheses, otherwise, right, you'll incorrectly, possibly incorrectly do something there. Okay, so there it is. I hit enter, and I get my first iteration for x of 1. 2 point, and it looks like 1, 2, 3, 4, 5, 6, 7, 8 sixes. And then a 7. Of course, the calculator is rounding off the digits itself, right? So it only goes out so far. All right, and so now then we can go, this is x of 1. What's x of 2 going to be? Well, we're going to plug in x of 1, right, minus f of x of 1 or f prime of x of 1. But our shortcut in the calculator is to do entry, to recopy that command. Now we're plugging in answer being the value of x of 1. And so x of 2 is this, 2.645833333. Okay. So again, I'm only accurate, looks like, to potentially the first decimal place. Again, we're going to the 7th decimal place in this one, right? Estimate the root to the 7th decimal place. But we know the trick from now on, right, is to simply hit entry in the calculator, to recopy that, plug in the new x of 2 in, and there's our x of 3. And it looks like we're up to maybe 3 decimal place accuracy, so I'll do it one more time. Second entry. And that's pretty good there. X of 4 gives me 2.645751 311. So it definitely looks like we're accurate out to there. And so what's our estimate for the square root of 7? It's about 2.6457513. If I go out to 1, 2, 3, 4, 5, 6, 7 decimal places, there's our estimate, right? How good of an estimate do we have? Well, let's just see what the calculator does if we just do the square root of 7, which we know. Now, I'm not sure how the calculator does this, if it's using Newton's method or some other algorithm. There's other algorithms for finding roots. But when we do that, notice it's exactly what we got with our fourth iteration of Newton's method. Okay, so again, programming, calculators and computers to do this sort of thing is very helpful. We take it for granted not just on square roots, but lots of things, you know, how to find the log or natural log or sine or cosine of values. All those things, there's algorithms to generate those things. And so it's a very important process, and you can maybe see a little bit in this how Newton's method helps. Okay, so that is the end of Newton's method and the end of the video.